I am actually really glad for going over cross-pricing mountains for cross-pricing. I remember dot product actually already, but like I never actually got cross-pricing with all the time.
It's right there. Anywhere. Yeah.
Because I mean, like, you can.
For clarification on mine and Luis's, we work together, so we have it. Mine is Mark Hunter with Luis. Is Mark Luis.
Okay.
Just because I just realized in case it's not clear.
I think I probably recognize y'all's handwriting. So.
We're there at the same time.
Oh, I did mine works.
Oh, then I won't recognize your handwriting. Then I'll recognize your.
I'm gonna go like talk to her real quick, see if he has a stage.
Go across the hall right there. Yeah. Yep, just right there into the lab. Yeah, cool. Look forward to seeing that.
Isn't that how it is? Just the words.
I feel like I'm right on myself here.
Is this your phone number on here?
Yeah.
Did you see my message I sent?
When? Today? Yesterday? I'm usually really good with my texts, so do you know about what time?
It was at 12 p.m.
Tuesday, right? Yesterday was Tuesday. These are the only messages I have from Tuesday. I only have 3 text messages.
That's so weird.
Is it an iPhone? Sometimes they don't show up till like...
I'm going to send you one right now.
Yeah, send it, see if it comes through.
Well, for one,
I also, I restarted my phone yesterday, but usually it'll come through.
Yeah, it went through as green. I don't know why. Does it usually do that for people?
I don't know.
Yeah, I just sent you a slash.
Okay.
Yeah.
Oh, I got it.
You got
I got it, but look, if you... Oh, wait a minute, hold on. It did come through from yesterday, hold on. But I didn't see it until right now. Like it didn't show up.
Okay, no worries.
Sorry about that.
okay.
Next time, just call.
Okay.
Yeah, sorry. Yeah, I have a Samsung.
Oh, you do? Okay.
Yeah, that may... Sometimes that happens.
Do you not like Apple?
They don't... I used to not, but I'm starting to like get to that point. Yeah, I mean, it's a give and a take, right?
The only thing I miss about my iPhone is FaceTime.
Yeah.
My sister and I use FaceTime 24/7.
It used to be that you could really, the customization was a lot better with Android, and yeah, whatever.
with phones, I use YouTube and I call people.
Yeah.
That's all I do with my phone. That's all I have.
Yeah.
I don't take photos either. So.
I trying to share video and stuff with people from Apple to Android. It's terrible. Yeah. All right, let's get started. The test is due. It looks like everybody has turned in the exam. Any last call? You're good? Everyone's good? You got it? Okay. All right. So give me a little bit of time to grade these. Hopefully I'll have these by next time that we meet. All right, that's my plan. We'll see. All right.
Quick question. What was the percentage of those were?
What?
The mini exams total.
I don't remember.
Okay.
I don't remember. Yeah. Yeah, it's enough that you care. Yes. Yep. Okay. Today is the 8th. All right, everybody's turned in. I'm going to pass the sign-in sheet around. I keep forgetting to do it, but I'll do it today. So last class we were talking about the vector functions, right? We had started chapter 10, section 7, And we had done this problem where we found the intersection of two cylinders, right? We found the vector equation of the curve that represents the intersection of those two cylinders, which is pretty interesting that we can do that with relative ease. We're going to continue into this section, and the next part just talks about how, with computers these days, we can actually graph things. We don't need a graphing calculator. We can just go to GeoGebra is the one I'm using for three-dimensional graphing, and you can graph curves and vector functions in three-dimensional space. So this is an example of a pretty complicated one. This is called a toroidal spiral, and all it is a torus. A torus is basically a donut, and it is the path is like a coil around that donut, and the vector function for that is pretty complicated. And this is just, again, to show you, this is the curve, this is how you type it in, and this is what you get if you go to GeoGebra and type that in. You get the weird kind of looking toroidal spiral, all right? And then another example is this trefoil knot, however you want to say that. All this is it's a strange curve because it's a curve that if you were to follow the path, it ties a knot on itself. Like if you were to pull it tight, it would be a knot. So kind of interesting. Again, just to show you, we can visualize these vector functions. All right, please turn in your exams. All right, the next idea here is derivatives. Yes?
What's the formula for the trefoil knot?
It's
That's just
it's not going to be pretty, but let's see. It's this right here, so all of that. Yeah, it's not a simple thing that we could come up with. All right, so now we talked about derivatives, right? We first talked about vector functions, then we talked about continuity, now then we talked about limits, and now we're talking about derivatives. So the good news is that if you have a vector function, remember you're either going to have 2 or 3 component functions in the vector function, either 2 or 3. And if we want to differentiate the vector function, we use the same notation from Cal 1. We do r prime of t. And all it is you just take the derivative of each of the component functions. That's it. So there's nothing new. And if there's 3 components, you do 1, 2, 3, you do derivative each one. All right? Now, what is the geometric meaning of that derivative, right? That would be the next natural question. And we know that in Cal 1, if we have a function, you take the derivative, it represents the slope of the tangent line. Well, if you have a vector function that's in 2 or 3 dimensional space and you take the derivative, what is it that you're getting? Well, first thing we need to understand is that the derivative of a vector function is itself a vector function. Because when you take your derivative, right? When you take your derivative, either one in 2 or 3 dimensional space here, you still have a vector, and that vector is made up of functions, which are just the derivatives of the original functions, right? You ready? Right here. Yeah.
I didn't have a staple.
You have to have a staple.
Can I
Go get a staple. Yeah. All right. So we get new vector functions, right? Just like in Cal 1, if we start with the function, we take a derivative, we get a function, usually, right? So everything is kind of as we would expect. The question is, what is it though, right? What is the geometric meaning? Well, if we're given some value of t, and we plug that t into the derivative, right, then we should expect to see a vector, right? And that vector is going to be a vector that is tangent to the curve at some particular point. So I have a visual for this. In blue, you will see there a vector function, right? And that is the vector function. Do I have it here? Yeah, this is the vector function r of t equals t sine t, t cosine t. So I've drawn just a little bit of it. I didn't draw the whole thing, just a little piece of it. And what I'm doing in red is showing you what the derivative is at various points in time. So for different values of t, I'm showing you the derivative. So at 0, at time is 0, the derivative of this particular blue curve is a vector, and the vector is the vector 0, 1, which is that vector pointed straight up, right? If I change the value of t, what's going to happen is I'm going to get a new vector. And those are the vectors that you would get. So the black vector is the original vector function, r of t. Remember, vector functions draw vectors, and the tips of those vectors trace out a curve. So the black vectors are creating the blue curve, and then the red vector is the derivative, and I'm just moving it and attaching it tip to tail. Now, that vector in red, the property that it has is that it will always be tangent to the curve, no matter what. It'll always be tangent. And that's kind of what we had in Cal 1, right? I mean, we had kind of a slope of a tangent line, right? But it was tangent line. So that's what we should expect to see here, and that, in fact, is what happens. So let's go ahead and just do an example. We're going to do that example. First thing we're going to do is we're going to find the derivative of this vector function, right? This should be straightforward because I just need to calculate the derivative of each of the component functions. So I'm going to call that the f function. I'll call that the g function. And so all I need to do is take derivative of each one and throw it into a vector. Let me move out here a little bit. So the first component is going to be something, and the second component is going to be something else. When I differentiate t sine t, I have to use a product rule, right? So I'm going to have derivative of t with respect to t is 1, then times sine t, and then plus the derivative of sine t is cosine t, but then I multiply that by t, and that finishes off our product rule for the first one, right? Now I move to the second one, and I do the same thing. So do y'all see this is like there's nothing, no new technique that we need to know. We just need to know how to do a product rule here. So on the second one, when I do a product rule, derivative of t, again, is 1 times cosine t. The only difference here now is that when I take derivative of cosine, I get negative sine. And so I'm going to have a subtraction, and then t sine t. There it is. That's the derivative. It is a vector function, right? Now, the next question says to take this. Let me move this up. The next question is to take this and find the vector which is tangent to that curve at t equals pi over 2. So that just means take our derivative, right? This is our derivative, and evaluate the derivative at pi over 2. And that should get us the exact vector that's tangent to that curve at that point. So r prime of pi over 2 equals, all right, we need to know our values of our trig functions at common angles. So sine of pi over 2 is 1, right? Plus pi over 2 times cosine of pi over 2. Cosine of pi over 2 is 0. So that's just 1 right there, right? And then if I plug in pi over 2 here, cosine of pi over 2 we just said was 0, minus, okay, this is pi over 2 times sine of pi over 2 is 1. So we should get negative pi over 2 there. That all right? That's just plugging in, plug and chug. That's a vector, right? And if we were to take that vector, two-dimensional vector, and we were to move that vector where the tail of it was at the origin, it would go to the right 1 and down pi over 2. So we should expect it to be like pointed in that direction. And I can verify that for you by looking at the curve here and actually going to pi over 2. No, yes, okay, I will. Pi over 2. There we go. There's the actual vector. That's the vector, but we've moved it. Instead of being at the origin like this, I've just moved it over and I've attached it to the actual point on that curve at t equals pi over 2. Okay? All right, now, what's the next thing? Find the vector equation of the line that is tangent to that curve at t equals pi over 2. So all we've done right now is we have found that red vector, right? I now want to find the vector equation of the line that passes through that red vector. So this line right here that continues in both directions forever, I want the vector equation of that line. And from the test and from homework, you should all be comfortable with the idea that the vector equation of a line, you need a point on the line, you need a direction vector, right? So a point on the line would be, we get it from there, and we would get it from this vector right here, right? That vector would take me to the point. And then to get the direction, well, the red vector is the direction, right? That red vector is the direction vector of that line. So the derivative is what gets us that direction vector. Make sense? Okay, let me do the work. That was just a visual. All right, so we run into one little problem here. R of t is the curve, isn't it? So I can't use R of t again because I'm talking about a line. This is something different. So what I'm going to do is this. I'm not going to call it R of t. Let me call it, I don't want to use, what do I want to use? I'll call it W of t, right? W of t. This is going to be the equation of the vector equation. This is going to be the vector equation of the line tangent to my R of t function at t equals pi over 2, at that point in time. So using the same notation we used when we were studying lines, I know that this is what I'm going to need to generate here is some vector I start at. I'm going to call it W naught plus t times v, which is my direction vector, right? So this is a vector that represents the one point on the line, and this is the direction of the line. Got it? So let's start with W naught. That has to be a point on the curve at the place we're talking about, right? So to get W naught, who wants to raise their hand and tell me what I do to get W naught? Just want to see who wants to play. I'll start with Hunter. This is going to be yours. We're one for the day.
Oh,
This is your one for the day.
all right.
All right.
We would plug in pi over 2 into our original equation.
To the original, right? To the original. Because I want to figure out where we are on the curve. That's one point on this line. So how would you write that, Hunter? Just notation-wise, I'd write
Be
like R of
r of pi over
pi over 2. Yeah, exactly. So I want to plug pi over 2 into the original vector function. That's going to give me a vector, and that's going to be that W naught vector. Now, pi over 2 into the original, I've already erased, or not, I've moved the original off. Do y'all remember what it was? It was t sine t, t cosine t, right? So this is going to be a vector. This is going to be the vector t, which is pi over 2, sine pi over 2, and then t pi over 2 cosine of pi over 2. And that vector, we know sine of pi over 2 is 1, cosine of pi over 2 is 0, so we should just get the vector pi over 2, 0. That is visually, not visually here, visually, that is this vector right here. Sorry, there's so much crap up here. That is this black vector, isn't it? That's that black vector. And it makes sense. It goes to the right, pi over 2, doesn't go up or down. So that takes me to the point. And now I'm going to get the direction vector. But the direction vector we already calculated, didn't we? When we did this right here. Let me get this out of here. So for V, V is the direction of this line. The direction of the line is same as the direction of the tangent vector, which is just that. So don't have to do any work. It's already there. And now I put it all together, and I get my vector equation of my line, which is W. You know what I forgot to put here? I apologize. This should be W of t. I forgot to put W of t here because this is a function of t. So W of t equals, all right, my starting point plus t times my direction vector. And then I can combine things together, right? If I wanted to, I could distribute the t through, and then I could put it together. I'm just going to leave it like that. If I ask my computer to graph that, I should get that dotted line. Yes?
Quick, is it possible, like, as a general rule, is it a possibility to turn a vector function into a normal function? Or is it that these are things we can't achieve with normal functions?
Well, you can, when you say normal function, are you talking about a normal function in like two-dimensional space? If we're in two-dimensional space, this can all get converted over pretty easily. But once you get higher than that, it's not as simple to go back and forth between the two. So,
Okay.
all right, good, straightforward, no questions? It's just using the tangent, yes?
I just had a question about the direction vector.
Yes.
Why did we use the values 1 and negative pi over 2?
Okay, let me go back to the picture, and I have to erase all this.
I think I was writing something down.
Okay, yeah, no, I mean, I want y'all to ask questions. Okay, this red vector is the tangent vector, r prime of t. And if we want to know the vector equation of this line, then for a line, I need a direction vector. I need any vector that points in the direction of the line. But that derivative vector, right, actually does exactly that. It points in the direction of the line I'm looking for. So I'm going to use that vector, which we calculated to be, what was it, 1 negative pi over 2? Right, 1.
Well, that's why I'm asking, like, why did we use the one with specifically the value of pi over 2?
Oh, because the question asks us to do that. The question says, find the vector equation of the line tangent to this curve at that particular point. Good? Okay. I want these types of questions because this is the way it is in math, right? Like if you're missing one little thing, everything seems like voodoo magic, right? But once you start to like understand, oh yeah, then a lot of times it's easy to resolve in your mind. All right, now we go to a new definition, all right? We have this idea of a tangent vector, right? R prime of t gives you a tangent vector on the curve. And since it's a vector, we know that we can do something with vectors. We can always find a vector that points in the same direction, but has a length of 1. So visually, this is what I'm talking about. What you see here is that same animation we had a second ago. The red vector is the derivative that we were just talking about. And notice that for every red vector, at every point in time, I can always find a vector that points in the same direction as the red vector, right? But always maintains a length of 1 the whole time. This becomes useful later, all right? So we need this later, so we have a name for it, and we want to know how to calculate it. And we do something that you may recall if I write it this way. If you take any vector and divide it by its own length, you get a new vector that has a length of 1. We did this a couple of sections ago. So we're doing the exact same thing here. We're taking the derivative of the vector function, which is a vector, and we're dividing it by its own length, and we get a new vector, and that vector is in fact, or does in fact have a length of 1. And we call this the unit tangent vector, and we denote it with a capital T vector. All right, capital T of t is your unit tangent vector. And this is actually a function, because at every point in time, you're going to have a different tangent vector. So we get a new function, all right?
Cool.
Go ahead. Yeah.
Okay. Is there a rate of change of that constant that we can go ahead and find?
A rate of change of what constant?
Constant is the one that produces the amount of magnitude of the length of the vector. As you continue on, it grows and shrinks. Is there a rate of change?
Well, that would have something to do with like a second derivative, because that's the rate of change of the rate of change, right? So it would be tied into the second derivative. All right, so let's do it for the problem we just did.
Cool.
All right, we have this vector function, and I'd like to find capital T of pi over 2. Capital T of pi. So that vector that we just found, that red one, I want to now find the vector that's pointing in the same direction as that one, but with the length of 1. So by definition, what I need to do here is take the derivative of the vector function at pi over 2, and I want to divide it by its own length, the length of that vector. And that vector was the vector 1, negative pi over 2, right? That's what we calculated. And we're going to divide that by its own length. So to find the length of a vector, at least a two-dimensional vector, you take the square root and you take the sum of the squares of the components. So this is this vector 1, negative pi over 2. And I'm dividing it by square root of, now I'm not going to go to my calculator and get a decimal or anything. I'm just going to write 1 plus pi squared over 4. So I just square that, add them together, I get that number, right? Now it's important that you understand what this notation means. This really means that I'm taking the number 1 over the square root of 1 plus pi squared over 4, and I'm multiplying it times the vector 1 negative pi over 2, right? That's what this really means. And then I can pass this fraction into the vector, and I still have a vector, right? It's still a vector, but I guarantee it's pointed in the same direction as the original one. It's just now been shortened to have a length of 1. So I'm going to pass it through, and I get 1 over square root of 1 plus pi squared over 4, and then comma, negative pi over 2 over the square root of 1 plus pi squared over 4. That vector is a vector that points in the same direction as the original tangent vector. It has a length of 1. That's it. Yes?
Does that unit vector work at all points, or do you have to find a new vector, unit vector for
Every point in time would have a different tangent vector. Yep. Yeah, because you can see that from the animation, right? Like right now, here, you see that we have this vector here. That's our tangent vector, but if I go, back in time a little bit, that's definitely a different vector. It still has a length of 1, but it's pointed in a different direction now. So at every point in time, you would have a different vector. Well, in general, there are certain curves that would be the case that the tangent vector is always constant. Yes?
So could you solve for the magnitude in general for t? First, or could you do that and then make a substitution?
Could you solve for the magnitude of
Like
t?
you just took r prime t over the magnitude of r prime t, did that, and then did the substitution at the end. Could we just do that?
Oh, you mean do it generally?
Yeah, do generally.
Yeah, so we could have done that. It would have been a lot more work. What's being asked, I believe, is could we have gone to this, taken its derivative, but not plug in pi over 2, right? And then take its magnitude and not plug in pi over 2 and get like a master formula for capital T, and then from there be able to do it for any t. Yes, I didn't do it that way because that's a lot more work algebraically, but it's definitely something we could do. Yeah.
And taking magnitude is the same thing, just t. It's
Take,
still like just square root.
yes. Mm-hmm. Yep. Okay, we move on. This is a different example. I'm asking basically the same question I just asked in the previous example. I want to find the equation of the line, the vector equation of a line that is tangent to that vector function, that curve, at a particular point, right? So, hey, what's up? Got your test? All right. All right, so if y'all are going to be late at all on a day that a test is due, please let me know ahead of time, all right? Because to me, that's, like in theory, that's an advantage that someone has if they have an extra 30 minutes, hour, right? I don't like that to ever happen, so, okay. All right, so what's the difference between this problem and the one before, other than the fact that it's a completely different vector function? It's what? It's in three-dimensional space, okay? So now we're going to do the same exact stuff, but we have to keep in mind that we're in three-dimensional space, so we just have to, do a little bit more work, but thank you. All right, so let's start cranking this out. Also, let me point out, before we get too far into this, I've given you the vector function that lives in three-dimensional space, 3 space, R3. You'll hear me say that they're all the same. Okay, so this lives in 3 space. And I'm not giving you t, am I? Not directly. I'm actually giving you the physical point that I want to find this tangent line. In the previous example, didn't I give you the value of t?
Yeah.
So here, I'm not directly giving you t. I'm indirectly giving you t, because what we're going to have to figure out is what value of t will get me to this point, right? What value of t gets me there? So we'll resolve that in a second, but let's just do the actual work. All right, so here we go. I need the derivative first, right? I need the derivative first. Shall we do it this way? Let's do it this way. Ultimately, here's what I want. I want a vector equation of a line, right? That's what we did in the previous problem. We need the vector equation of some line. This W naught is going to be my original vector function at some point, right? At some point. And I need to know what that point is. I need to know what that t is. So what I'm going to do, this is a very simple example, because if I want to know what t I plug in here, here, and here to get these 3 values to come out of the component functions, you can just look at the last component. Look, the last component is t. And so I know that t must be pi over 2, right? But let's act like that wasn't there. If that wasn't there, then what I would need to be thinking about is, what do I plug in for t to make this a 0? And then I start thinking, okay, well, what would make 2 cosine t 0? And I say, oh, well, if t is pi over 2, right? And there's not a unique answer. There's infinitely many answers, but you'd be trying to mess around and see if you could get these to both happen at the same time. Fortunately for us in this example, it's very easy to see what t is. Right? And I believe in no problems that you're going to run into in this class will there ever be an ambiguity where the t is not uniquely defined, where it could be multiple values of t. So you should be able to deduce what t is in every problem you see. So let me put up here, t is pi over 2. All right. And then this right here is going to be the value of the original vector function at pi over 2. And then this is that direction vector, right, for the line we're looking for. And that should be what? Thank you. The what?
The derivative of the r.
The derivative of the r at pi over 2. Right? So if I get this, I get that, I have the vector equation of the line, I'm done. So we need the derivative, right? So let's take the derivative. This derivative should be straightforward, I hope. There's not even any product rule in this.